Well, hello there, and how are you today? Nice to be with you. We're going to continue our marvellous journey into the spooky land of the complex number today, and we're going to continue with our modulus and argument form of the complex number which we covered last time. And today we're going to look at basic operations on complex numbers in modulus and argument form. So let's get into it, guys. Now, the first thing we're going to cover here is addition and subtraction if they're in modulus and argument form. Now, this is the one situation where they're not very useful at all. Okay, so if you have to add or subtract complex numbers which are in modulus, argument, or polar form, then don't bother. Put them in Cartesian form, and then you can do it easily. Okay, so there's no easy way to add subtract in polar form. However, don't worry, just about everything else you can do with them is marvellous in polar form. So it was useful to learn it last time, and you'll find out later in this video it's absolutely fantastic to do when they're in polar form for just about anything else besides addition and subtraction. Now, therefore, we convert them to Cartesian form, and then we add and or subtract as required. Okay. Now, firstly, let's take 2 pi on 3. Okay, that's our first one. And of course, we're going to draw a diagram to work out how to put that into Cartesian form, because, as I said last time, you'll be hazy if you're lazy. So don't be lazy. You'll drive us all crazy. Now, okay, there it is. It's quadrant 2, and we've got, what do we got here? 2 pi on 3, now that's the angle, the sweeping angle from the positive direction of the x-axis right round to the red line. If you imagine this little point here is a hinge, okay, hinge, and we're sweeping around to, just like opening a door, round to that point there. Okay, that's 2 units long. So now we're going to work out, with our trusty cast diagram, of course this angle in here would have to be pi on 3, and that's the critical angle that we need, the sine and the cos of. And cos in this quadrant will be negative, and sine in this quadrant will be positive. That's the deal. Okay, you're well used to that by now. So it's a quadrant 2 angle, and we've got, we're expanding out our cis notation, 2 times cos of 2 pi on 3 plus I sine of 2 pi on 3, which for you and me is going to be cos of pi on 3 is, what is it? Yes, it's a half, and sine of pi on 3 is root 3 on 2. You knew that, didn't you? You better jolly well know it. You have to know it, guys. And that's it. So now we're ready for action. Lights, camera, action. Here we go. That's very good. Now, and we're cancelling out the 2's, and we're getting minus 1 plus root 3i. That's the Cartesian form of that little gremlin there, okay, this little beast. Okay, 2 pi on 3 is also otherwise known as, aka, minus 1 plus root 3i. My oh my. Now let's do the second one now. What was it again? It was 3 cis minus pi on 3, wasn't it? Okay, yes, draw a diagram. Draw a diagram. Now that's a quadrant 4 angle, isn't it? And a very nice specimen. So let's just go with that. And it's same old cast diagram. Cos is positive in that quadrant, so it's going to be 3 times cos of minus pi on 3 plus I times sine of minus pi on 3. And of course, cos of pi on 3 is positive, and it's going to be plus a half, and sine of minus pi on 3 is negative. It's going to be minus root 3 on 2, but I'm getting ahead of myself. Here we go. Yes, don't you know? There it goes. Very nice result. Now we've got to do what we were originally asked to do, which was up here. We've got to get 2 of these and subtract 3 of those. Okay. So, but we can do it now because it's in Cartesian form. That's what I'm saying. Oh yes, a little bit of finality there for that one. Now let's do it. So we've got, there we are. We've got that statement. And we've just got to get rid of that bracket in the second term, and then be very careful adding those up. There's a bit of mental gymnastics involved in getting it all. You've got, what have you got? You've got minus 1, which is minus 2 on 2, minus another 3 on 2, gets us minus 5 on 2. Now we've got root 3i plus 3 root 3 on 2. So you could call that 2 root 3 on 2, couldn't you? Then you add another 3 root 3 on 2, you get 5 root 3 on 2i, and I think we need a box. Thank you, Mr. Box. So that's how you do it, guys. So can you please remember, adding and subtracting is a dead loss in polar form. Just do it in Cartesian form, okay? But everything else in this video, you are going to be amazed, because it's marvellous, and polar form is well worth learning for that reason. Now, okay, multiplication by a scalar. Okay, scalar just being a number, so if we had to say, if z was 2 cis pi and 3, and z2 was 3 cis of minus 5 pi and 6 apparently, we've got to find 2 times z1. Now the scalar, spot the scalar, there's the scalar in that one, it's 2, and the scalar in this one is minus 1. Okay, now that's a tricky one. You've got to watch him very closely. He's a bit of a trickster, this one. Now, let's go. Now, as you could, well, yes, of course you have to draw a diagram. As you could imagine, 2 times z1, what is it going to do? Let's put z1 in first. There it is, 2 cis pi on 3, right? Now, if you have 2 times that, come on, imagine, what is it going to look like on the Argand diagram? What do you think? Yes, of course it is. It's just going to be twice as long, but in the same direction, isn't it? Yes, it is. So it's going to be that. Yes? So, it's going to be 4 cis pi on 3, isn't it? Of course it is. Yes, of course it is. Now, the next one, though, however, is a trickster. You've got to watch him. Oh, yes, so well, just to finish off on this, the length is doubled and the angle is unchanged, all right? Now, yes, Mr. Box. Thanks, Mr. Box, and hello to you today. Now, B for you and me, okay? And you will see that he's a bit tricky. There is, in all its finery, 3 cis minus 5 pi on 6. Do you agree with me? Yes, you do, don't you? Right, now, but the thing is, if we do minus that, what's that going to do to it, guys, on the Argand diagram? What is going to happen? Yes, it's going to go exactly diametrically opposite, okay? That's what minusing does, yes? Okay. Right, now, but what is the angle now? What is the angle? The length is the modulus is the same, but the angle is now, yes, the angle is now pi on 6, okay? That's what I wanted you to notice, okay? So, if you don't draw a diagram, well, you know, I don't know how you're going to work it out. So there it is, that's the answer. So, in other words, in this case, the length was unchanged, again, but the angle changed. The angle changed by pi. In fact, a nice little rule I'm going to talk to you about on the next screen is that if you have to reverse the thing like that, a minusing thing, if you've got a negative angle, you add pi. So minus 5 pi and 6 plus pi gets you pi and 6. Very nice, isn't it? If you have a positive angle and you have to go in reverse, if you had pi on 6, you would take pi, you would subtract pi, but I'll do that over the screen, okay? Right, so that's the deal, okay? Happy? Right, let's go. Now, in general, if z equals r cis theta for this kind of situation multiplying by a scalar, we're just going to try and summarise in general terms, but I think you already understand. K times z, where k is the scalar, has the following effect. It depends on whether k is a plus k or whether he's a minus little beastie. If he's a minus, he's a trickster. If he's plus, he's very, very innocent, okay? So you don't have to be careful of him. So the modulus r is scaled up by the factor of k, of course, as we just discovered. It's, in other words, the line is twice as long or 3 times as long or whatever k is. The argument, however, is transformed as follows, right, as we were discovering in the previous screen. So what we find is that if k is positive, it's no problem. He's benign, he's innocent. The argument of z is unchanged. However, yeah, okay, if argument of kz is just the same as argument of z. If you think about that, you will understand, okay? Now, if k is negative, you have to be a little bit careful, okay? Argument of z changes to its diametric opposite position, right? Now, If the argument of z is negative, then basically you add pi, okay, to get yourself into the positive land. And if the argument of z is positive, you subtract pi, okay, to get yourself into negative land. That's what you do. But look, if you just draw an Argand diagram, you won't have any problem. You'll understand what to do. Of course you will. Now let's just do some examples just to make sure we understand this. If z1 was 2 cis pi on 3, 2z1 would be 4 cis pi on 3, wouldn't it? Yes, it would. We wouldn't change the argument, but we would scale up the modulus. That's what we know. What about if z2 was 3 cis minus 5 pi on 6, right? Negative argument, right? Now, what are we doing now? Ooh, trickster, trickster. So minus 2z2 will be, we scale up the modulus to 6, and then if we had to reverse that one, we add pi. So minus 5 pi on 6 becomes pi on 6, right? Now, here's one with a positive argument. If we had z3 was 4 cis pi on 3, we'll do a trickster one on that. Minus 2z3 would be 8 cis minus 2 pi on 3, because if we're in positive land here, this little beast is positive. If you have a minus here, the trickster one, you've got to basically subtract pi to honour the commitment of the minusing here, okay? Do you know what I'm saying? Yes, you do. Yes, you do. Okay, very good. Okay, we can move on now, can't we? Good. Okay, multiplication of complex numbers in polar form. Now, I hope you've got a chill pill ready, because this stuff, it's theoretical, but it's absolutely marvellously stunning when you see the results of it. So I wanted to do the theory, just not to bamboozle you with algebraic waffle, but to just amaze you at how beautiful mathematics is. Now, okay, we've got two little unsuspecting little numbers there, R1 cis theta 1 and R2 cis theta 2. They're going to have an amazing dance together in a moment. Have a look at this. Z1, Z2. Now, look at this. What is the result of multiplication of numbers in polar form? Now, we're going to expand out the cis notation here, and you're going to see something truly, truly marvellous. Yes, now, guess what I'm going to do now, guys? Have you got that chill pill? Come on. Good. Swallowed it. Let's go, because we have to multiply these brackets out and get a result. And it's going to be a rather amazing proliferation of stuff everywhere, right? Watch. Now, first of all, you multiply those two terms and you get that, right? Agree? Right? Okay, now we're going to do the next two, and what are we going to get from that? We're going to get I times cos theta 1 sine theta 2. Now, okay, the next two now. Okay, what's that get us? Gets I sine theta 1 cos theta 2, and then the last one gets us I squared, which is minus 1, minus sine theta 1 sine theta 2. Now, goodness, let's gather up our ducks in a row, get the reals together and the imaginaries together now. Now look above, you'll see me tick them off, right? There's that one. Okay, now the next one is the other one. That's the fourth term, the last term, tickaroonie. Now the two imaginary ones now, I times, now that's this one here, isn't it? Wait a minute, what is it? Is it this one? Yeah, sine theta 2, yes, just with the terms reversed, yeah, okay. There it is, yes, and the last one is this one here, there, that one there. Yeah, with the terms reversed, but it doesn't matter. Yeah, okay, now, all right, now what have I done to you? No, just settle down, it's all right, because this is, I'm just closing the bracket now, this is, that's what that comes to, because, ladies and gentlemen, this is a compound angle formula. Depending on where you are in the course right now, you may or may not have got to this yet, but it's a compound angle formula, and if you expand that out, that's what you get. That's what you get, right? And the same thing with this one here. If you expand that out, that's what you get. That's what you get. Now, have a jolly good close look at this. What have we got? This is cis. Good old sis. There we go, look at it. Now, you might be sitting there in a blur thinking, well, what the? No, look, I'll summarise what I've just done. Thanks, Mr. Box. Because when you multiply complex numbers, Z1 and Z2 together, what you do is you multiply the moduli together, as I've done, R1 times R2, and hence the new modulus then becomes R1 times R2. And what else do? You add the arguments together so that the new argument becomes theta 1 plus theta 2. Ain't it marvellous? Ain't it marvellous? So that's what you do. That is the end result in that box there, okay? So if you multiply two numbers together which are in polar form, you have to multiply the moduli and you have to add the arguments, okay? Right. Truly amazing. Now, we're going to do some more of this. Now we're going to do division in the same way. So now, ready, here they are. Here are the two little candidates ready to have a wonderful complex dance together. Right, Z1 over Z2 would be this, and it looks horrendous, doesn't it? However, don't worry, because what we can do is what we always do when we have complex number with an imaginary part on the denominator is we rationalise by multiplying the top and the bottom with its conjugate. Yeah, it's Z bar, right? Now, excuse me. Now that looks horrendous, but it's not as bad as it looks. Its bark is worse than its bite, right? Because the bottom line, remember, is a difference of two squares now, and that just becomes something truly lovely. Let me demonstrate. Now, we've got to multiply the top out. We've got to do the same old thing with the top. Okay, ready? Let's go. Those two, we get that, yeah. Okay, next two, we get an imaginary part. That looks right. Now we'll do the next two. Okay, that one, that's another imaginary one, isn't it? Yes. And the last one is an I squared minus I squared, which will get us a plus sine theta 1 sine theta 2 for me and you. Good. Now that's beautiful. Now you watch the bottom line. Look at this. Now, what is sine squared plus cos squared, or cos squared plus sine squared? Yes, it's 1. What a blessed result. Don't you love that? I do. Truly love it. Right, now we're going to, for the top line, we're going to get our ducks in a row, get all the reals. I'm ticking them off as we go. Have a look at north. There, that's the first one. Now, okay, this is the other real one, which was on the end. That's over here. There. Okay. Tick him off. Now we'll do the two imaginary ones, right? Plus I times. Now that one is that term, the third term, and now here comes the second term now. Good. Now this is very good. It looks similar to what we got on the previous screen, except that on the previous screen, ladies and gentlemen, this was a minus. I'm not going to go back and show you, but that was a minus, and this was a plus. So the signs have reversed in between them. So what that does, in terms of your compound angle expansion thing, I've just closed that bracket for you, what that does is get you, yes, instead of a plus in here, you get a minus. Instead of a plus in there, you get a minus. So it's the same compound angle stuff, which, as I say, you may or may not have got to on your course yet. But don't worry about that. It's awesome, and I never use that word lightly. So there you go. So now, what does all this mean? You were thinking? Yes, it's that. Cis again. It's cis. Good old cis. So it's the same deal. What's in that box is what's important for you to know, okay? So when you're dividing complex number, Z1 by Z2, you have to, the new modulus is R1 over R2. That's R1 over R2, dividing. And as you would probably imagine, the new argument is theta 1 minus theta 2 instead of theta 1 plus theta 2 in the multiplication one we did on the screen before. So that's what you do, right? That's what you do. Now, have a look at this. After multiplying or dividing complex numbers, as we've just showed you how to do, you must also adjust the new argument as necessary so that it complies with the naming convention for the principal argument. In other words, you might get something like an angle of 3 pi on 2 as a result of doing your multiplication or division, but that's not complying with the rules of our principal argument. So you'd have to rejig that to call that minus pi on 2. That's what I'm saying, right? Yeah. So there's our little ready reckoner for you to say that. So you've got to put it, if it's a quadrant 1 or quadrant 2 angle, you've got to go between 0 and pi. If it's a quadrant 3 or 4 angle, you've got to go from minus pi up to but not including 0, either pi, or either negative pi or 0 including, right? You get that? Yes, you do. Of course you do. Now, okay, so let's do some examples for you. Z1 is 2 cis pi on 6, apparently. Z2 is 3 cis minus 2 pi on 3, right? So we've got to find this one, multiply them together, and we've got to divide them, and we have to do something else for a special treat. Wow! Z2 squared over Z1. Goodness. Okay, well now we'll do the first one. That's A today. Hooray, here it comes. There it is in all its glory. Now, come on, the rules are we have to multiply the moduli and add the angles, don't we? Because we're multiplying them together. Let's do that. Now, I've put them into, probably didn't need to put them into twelfths, but it doesn't really hurt. I could have just put the second one into sixths, but it doesn't matter. Twelfths always seems to work, so I usually do twelfths. Pi on 6 is 2 pi on 12, and 2 pi on 3 is 8 pi on 12, so we've got minus 6 pi on 12, haven't we, guys? Now, minus 6 pi on 12 is minus pi on 2, so no need to rejig that argument. It's perfectly okay as it is, Mr. Box. Thank you, Mr. Box. Okay, that was a nice simple one, wasn't it? But it gets us into the swing. Righto, what about B? We've got to divide them now. Okay, so what would we do? We would divide the moduli and we would subtract the theta 1 minus theta 2. So we're subtracting a negative angle, right? We're subtracting, and now I'll put these ones into sixths just to not create extra work. So that's pi on 6 plus 4 pi on 6, which gets us 5 pi on 6. So that argument's all right too, no argument about it. So that's, we didn't need to rejig that, so the answer is 2 over 3 cis 5 pi on 6. Mr. Box, thank you. Now C fills us with glee. Now let's see what we've got to do. Z2 squared over Z1. Well, that's Z2 times Z2. So that demystifies what to do with the square, doesn't it? Over Z1. Now, let's take it carefully. Four-wheel drive mode. No mucking around here. No algebra heroes, please. So that looks like 9 over 2 for the modulus, doesn't it? Now that argument, goodness. Well, it looks like minus, we'll put it into, that's 2 and 2 is 4 pi on 3, which would be 8 pi on 6, wouldn't it? It would be minus 8 pi on 6, and then minus another 9, minus another pi on 6, which would get us minus 9 pi on 6, and now that's going to cause a non-principal argument. We'll have to rejig that. Yes, see, I was getting ahead of myself a bit. Now look, that's going to be minus 3 pi on 2, and minus 3 pi on 2. Now come on, get a little Argand diagram into your head and sweep it around. Minus 3 pi on 2. That takes us to the borderline between quadrant 1 and quadrant 2, which is actually pi on 2 in the principal argument terminology, right? So we've got to express that as 9 over 2 cis pi on 2. Okay? Do you get it? Very good. Okay, I think that's great. Now, let's do some more. Now we're going to multiply and divide complex numbers in. Well, we just did that, didn't we? No, but this is, wait for it, the geometric significance. Ooh, well, as if there was any more excitement. Yes, there is. Now we're going to do this. Do little diagrams because we need to do geometric for you. So there's Z1, and Z2 is 3 cis minus pi on 4. So what are we going to do? We're going to multiply them. Yeah, that's all right, isn't it? So that'll be 6 cis, well, that's 2 pi on 12 minus 3 pi on 12 is minus pi on 12. Yes, it is, isn't it? Yeah. Z1 on Z2 would be 2 over 3 cis pi on 6 minus negative pi on 4, which would mean pi on 6 plus pi on 4, which would be 2 pi on 12, plus 3 pi on 12 would be 5 pi on 12, wouldn't it? Goody, goody. Now, come on, we'll do some diagrams. Okay, alakazam, alakazam. Woo, gee, I'm a magician as well. So now, let's have a look. I've got them all ready made for you. There's your little Z1 sitting there nice and peacefully, minding his own business. There's Z2, and now we are going to multiply them on this diagram, and on this diagram here they are again, and we're going to divide. Okay, so what do you do? What do you do? Z1 times Z2. Goodness, look at that. So we multiplied the moduli. 2 times 3 is 6, so you get a much longer one, don't you? And the argument was the result of the addition of those angles. So we had a positive one and a negative one. The negative one was a little bit bigger in size, so we ended up with a net result of minus pi on 12. Get it? Now what about this one over on the right? Z1 over Z2, okay? So that's going to be, the length is 2/3, so it's only going to be a stumpy little guy. And it's cis 5 pi on 12, so there he is. Look, he's microscopic. He's microscopic, poor little fellow, look. There he is. He's only 2/3, and he's 5 pi on 12, which is only pi on 12 short of pi on 2, because pi on 2 is 6 pi on 12, isn't it? There he is. Now, because I thought this is a little bit pathetic, these diagrams, I decided to go for the full hog and do you some proper polar graphs. Now, no, it's not an eye test or anything like that. It's a polar diagram, and the features of it are that you can see all the scales here are the same. Like, you know, that's your 2, 4, 6 and so on. And these radial lines here denote separations of pi on 12 radians, so that there's 6 of those in a quadrant to make up 6 pi on 12 or pi on 2. So that's pi on 12, that's 2 pi on 12 or pi on 6, that's 3 pi on 12 or pi on 4, that's 4 pi on 12, which is pi on 3. Get it? And then this one's just 5 pi on 12, and there we have it. Now let's go with this. This is what we just did over the previous screen. 2 6 pi on 6, abracadabra. Whoa, look at that. Very nice, yeah? Does it look right? Yeah, it does. It's 2 units long, and it's 2 of those segments up from the positive direction of the x-axis, so that's 2 pi on 12, which would be pi on 6. Yes? Well, now we're going to do 3 cis minus pi on 4. Come on, where do you think it would go? Let's have a game here. Where would it go? Don't you know? Yes, I do. There. Did you have it around about there? Yeah, 3 units long, and pi on 4, which is 3 of those little segments clockwise from the positive direction of the x-axis. Now we've got to, if you multiply them together, we're going to get something 6 units long, and it's going to be minus pi on 12. Yes? Okay, let's do it. It's a red line this time. Oh, isn't that nice? Look at that. Beautiful. Okay, that's what you do. Now, if you get that in an exam, you will know what to do. Yes? Yes, you will. So the modulus was R1 times R2, which was 2 times 3, which was 6, and the argument was theta 1 plus theta 2, which got us minus pi on 12. Okay, here comes the next one for the division. Okay, so we've got 2 cis pi on 6. Now where would that, now this, the scale on this one's a little bit different, so don't be tricked, because I needed to be able to represent that poor little stumpy result for you. And so this one only goes up to 3, and so therefore everything's going to look bigger. Okay, so 2 cis pi on 6 goes there. Okay, now what about the next bit? 3 cis minus pi on 4. Now, where is it again? Well, we only got to look over on the left-hand side to see where it will be. Yes? Okay, it just looks bigger because the scale's, it's a more magnified scale. Now, but the result of the division is quite different, right? The result of the division is quite different, right? We got 2/3 cis 5 pi on 12. So imagine it. Come on, where do you think it's going to go? Well, there you are. Were you right? Good on you. That's terrific. Okay, well done. So the modulus was R1 over R2, and the argument was theta 1 minus theta 2, which, if you like, is theta 1 plus the negative of theta 2. Same deal, same thing. Don't you like those polar graphs? They're really neat, aren't they? So alright, let's continue on. Now, what are we doing with this? Okay, we're doing this beast, right? The algebra, we'll do the algebraic method, and then I'll show you on the, I think I'm going to show you on the polar graph as well. So the algebraic method would say, that is cis, 1 cis 0. Do you get that? That's what 1 is. A lot of students get very confused with that. 1 is just on the real axis, right? At 1. Coordinates would be 1 and 0. So it's 1 cis 0, guys. We're dividing that by 2 cis pi on 4, aren't we? Yes, that would be the result. Well, ladies and gentlemen, wouldn't it? Of course it would, okay? Do you see that? I want you to see that. Thanks, Mr. Boggs. Here's your diagram. Geometrically, it looks like this. Okay, so where are the little components? There's 1 cis 0. Hello to you. And what about 2 cis pi on 4, guys? Where will it go? Where are you going to put it? Come on. Yes? Good work. Good work. Okay, now the result was a half cis minus pi on 4. How interesting. There it goes. Look. Isn't that interesting? So when you divide, you always get a smaller little stumpy answer for your modulus, and and the angle is worked out as we've described. Well, I'm excited. Are you? Yeah, that was the modulus, and the argument was that thing. Now we're getting well used to this now, aren't we? Now the last exciting thing for today's extravaganza is de mois' theorem, and I apologise to Mr. de mois if I haven't got his pronunciation right. I get everything from de moiva to just about to anything, and I don't understand French, so I do apologise to all my French friends. That's de mois' theorem as far as I'm aware. So de mois' theorem is simply a corollary of multiplication of complex numbers in polar form, and it works like this. If you had z1 was r1 cis theta 1, yeah, okay, now we know that therefore z1 times z1 would be r1 times r1 times cis of theta 1 plus theta 1, wouldn't it? It would, indeed it would, and that really means that z1 squared is r1 squared cis 2 theta 1. Now, on the line below, I've said, alright, well let's take that a little step further. What about this result here multiplied again by z1? So it would be r1 squared times r1 cis 2 theta 1 plus theta 1. So what would it be? It would be, yes, it would be r1 cubed times cis theta 3 theta 1. Now, are you getting the pattern here with de mois' theorem? It's a really neat theorem. So in general terms, what we can say here is that if you raise r cis theta to the nth power, you raise the modulus to the nth power, and you just take n times the angle, where, yes, okay? Now, n times the angle, where n is an integer, okay? N is an integer. You get that? Not a complex number, an integer, all right? Z means integer. It's the set of integers, remember? Thanks, Mr. Box. Now, let's do some. Right, 2 cis pi on 6 to the 9, right? That would be, now come on, what would it be? Come on, before I say it. Yes, it would be 2 to the 9 cis 9 pi on 6. Now, we want to get that argument fixed. That doesn't look right. That's not principal anymore. So I'd say that would be, looks like it's 512, goodness, 9 pi on 6. Now you've got to think, what is that? That's 3 pi on 2. 3 pi on 2, if you just do a little sweeping thing in your mind of an Argand diagram, that takes us right from the positive direction of the x-axis right around to the minus, the negative imaginary axis, doesn't it? Which is in the wrong place for that notation, so it's in the under the x-axis, so it's minus pi on 2. Get it, Mr. Box? Thanks. You get that? That's, you've got to rejig some of those arguments. Now, what's this one? Goodness, this is to the minus 9. Well, it just works exactly the same. The minus doesn't make any difference with the de mois' theorem. So it'll be 2 to the minus 9 cis of minus 9 times that angle, okay? That's what it's going to be. Now, we've got to think about minus 9 pi on 6. Well, that's exactly the reverse of what we just did in the previous example, okay, where we just were over here. Well, now we're doing this one. So you've got to go sweeping around in a negative direction now from the positive direction of the x-axis for minus 3 pi on 2, which takes us to the pi on 2 axis, doesn't it? Yes, it does. So it's therefore, 1 over 512 cis pi on 2. Good, Mr. Box, thanks. Now, do you get de Mois' theorem? De Mois' theorem is mighty cool. Now, here's some more, and then we're finished. This is a long session. Alright, simplify A today. We've got cis pi, 5 pi and 6 over cis 2 pi and 3 to the 7th. Good heavens above. Don't worry, just do one line at a time. Inch by inch, anything's a cinch, but mile by mile is a terrible trial. So, here we go. Now, what did I just do, guys? What did I just do? That one's the same. This one here, well, it's 1 cis thingo, 1 cis this, so it's just the 1 to the 7 is just 1. And 7 times 2 is 14 pi over 3. Goodness. Now we can divide them in the normal way. So it's 5 pi on 6 minus 28. I've made it into sixths. So 5 minus 28 is minus 23 pi on 6. Now, goodness me, that's actually pi on 6 short of minus 24 pi on 6, and minus 24 pi on 6 is actually minus 4 pi. Yeah? Which just gets us right back to the positive direction of the x-axis. So I'd say that's just a pi on 6 in disguise. It is. Goodness, we worked it out. Okay? If you get confused with that, draw yourself a diagram and just go whizzing around revolution-wise till you understand what you're doing. Good. Okay, this one here now, we have to, that one there, we've got to put it into polar form because, you know, if you want to do that in Cartesian form, well, the best of British luck to you guys, but I'm not going to, okay? Because I want to save time, because exams are time poor. Yeah, and you've got to do it in the quickest time that you can and get it right. So, I've converted them into polar form for you in a flash. This one was root 2 cis of minus pi and 4, and you'll get that good at it too as well. To the 3 over this one here is 2 cis pi on 3 to the 4. Now that's a simple matter now. It just becomes, the first one becomes that, check it out, and the second one becomes that, check that out. Now that's easy. Now this this conundrum here, 2, well that goes into there, that becomes just 1 over 2 to the 3rd, which is 8. So this is going to be root 2 over 8. Now we've got to put this horrible thing into twelfths. That'll be minus 9 pi over 12, and that'll be taking away 16 pi over 12, I think. Excuse me. Yes, very good. So now we're going to work out what's 9 and 16. 16 and 9 is 25. Minus 25 pi on 12, which I think is minus pi on 12 in disguise. Isn't it? Yes, it is. My goodness, Mr. Box. Thank you, Mr. Box. Okay, getting it? Yeah, if you're not as quick as I am at doing those, you'll get as quick and quicker by the time you do a lot of practice, okay? Because I'm not practicing these all the time. I just know how to do them. But you have to practice them like crazy for your exams. Now, okay, so there we are. Now that was that's one. I just put that one in there because that's 1 cis theta. Yeah, don't be confused by these things. Just put it in polar form, guys. Anything can be put into polar form. Any number. And we're dividing that by 1 cis. I times that angle by 9. So that's going to be a simple matter of 1 cis 0 minus 18 pi on, minus 18 pi on 3, which will be just 18 pi on 3. 18 pi on 3 is 6 pi. And 6 pi apple of my eye is just 2 pi in disguise, which is 0 in disguise, which is 1. I think it's 1, isn't it? Ah, what a tricker. It was 1. And that's the end of the show. Alright, thank you for watching. Yes, we saw the light and it was very bright, and we're right. And we're ready to fight the good fight and go on and to victory. Okay, so we've done lots today, and you practice them now. Go ahead and practice them and have a wonderful time doing it too. And all the best to you, and we'll see you next time. Bye.